This is Mohammad Sadiq Rahman. So, as part of the requirement of artificial intelligence course, I'm going to discuss about our assignment 2 of reinforcement learning. That is about multi-armed bandits problem. So, in the assignment, we're dealing with four types of machine. It's just called machine 1, 2, 3, and 4. Machine 1 has the probability of 10% success rate, whereas machine 2 has the probability of 50% success rate, and machine 3 has 60%, and machine 4 has 40% probability success rate. So, multi-armed bandits is a problem that is, we'll just train a model to so that it can take some decision which machine to pick next for the maximum reward. So that's why let's start our program. At first, we are just importing all the necessary functions, numpy, random time, and so on. And each action has some reward. So if it is do some success thing, then we just correspond it to 1. And if fails to pick the best action, then it will be penalized, so that the reward will be 0. So at first we are just defining the reward function, and we're defining the time step. So we're taking any random number, and if this random number is less than or equal to the probability of the arm it wants to pick, and if the random number is less than that, that means we're ready to pick that. So reward will be 1, otherwise it will be 0. So by this way, we are just defining our reward function. And then we need an agent to work in the reinforcement learning, where he will work in the environment and it will get some reward upon its action. So we are just defining the class agent, and here the agent will perform some actions, and it has some quality values, and the quality value is nothing but the expected rewards of each action. So at first we're just initializing it to number of actions is equal to 0, and the total reward or quality value is equal to 0. And then we have to update the quality values each time after the agent does some action, and if it gets some reward, so we have to update the quality values. So we'll just counting the actions one by one, and it will get updated. And also we have to update the quality values by this formula that is given here, that is quality value, that is after a action, the total reward is qa, and if the immediate reward is of an action is reward a, and this is the quality value of the previous action, and na is the total number of actions, and by this formula the total action quality value will be updated. So and this is the formula to update the quality value of the action. And then we have to take some decision which action to be get, and that's why we are just defining some epsilon value, and the epsilon value has some range from 0 to 1. If the value is 0, that means there is no exploration, the total is exploitation. And if the epsilon value is 1, it means the agent will do more exploration. And so it will just by the upon the value of epsilon, it will continue to exploit or explore, and it will just take different actions and calculate the quality values and of all the machines, and it will get the maximum value of quality value, and it will choose that action. So his exercise 1, it deals with the episode function and the total number of action and reward value. So we're defining the episode, and that is it has two arguments, is probability and steps per episode, and it has some length of probabilities. As there are 4 machines, the length will be 4 here, and we'll just define total number of number of actions per episode and rewards per episode. So whenever the machine will get some action, it will be converted in action strategy based on its EPS value, and we'll continue to calculate the reward based on the probability of this machine and the action. And we have to update the Q values, and by this way, we'll just calculate the total number of actions and rewards. And so exercise 2 it deals with different values of epsilon 0 and 1 and the in between any values to find what is the output result if the machine, if the agent does some exploration or total exploration or the mix of the mixture. So here the example is the probability has some arrays of 4 values as there are 4 machines. So there are 4 different probabilities of each machine, and number of arms is nothing but the 4, that is the total 4 arms of this agent. And we're defining the maximum episode to be 1000, and steps per episode there should be 500. That means steps mean nothing but the action. So per episode we'll do 500 action of different machines. And for example, we are just defining EPS value as 0.2, and we'll just calculate. At first, we are just initializing the so what should be the steps per episode? That will be 500, and total action is 500, and the total number of arms is 4. So if we write some codes that takes some action based on the epsilon value, and it calculates the reward and average reward per time steps, and it just prints the average reward per time step after 100 time steps actually, and it just calculates the total reward, and it also calculates the actions of each machine, which is decided by the calculation of the maximum quality values. And if we run this code, we just get these values, and if you plot the result, then we'll see that as there are 0.2 epsilon value, that means there will be 20% of exploration, and rest of 80% will be exploitation. And that's why finally, whenever this is the episode length, steps per episode is 500, and whenever the machine tries different exploration and it finds that arm 4 is better in getting reward, so ultimately the average reward tends to the probability of the machine 4, that is up to 0.8 really. And if we plot the graph by which arm has to be chosen over the time steps, then we'll see that arm fourth number arm that has the maximum choice of 77%, and the rest of the arms are just given in the graph, and the mean average of choosing an arm is 77%. So let's see what happens if we do the total. If we set epsilon value to be 0, that means the agent will do 100% exploitation, and there will be no exploration. And if we run the code, then after each 100 times steps, the reward can be calculated, and we can see that from the graph, that is the average reward is 0.1. This is nothing but the probability of machine 1, and and if we run the graph of arm choice, and that will be in the total time, first arm has to be chosen because there is no exploration. And so only arm 0, that is first arm, has the maximum 100% probability of choosing, and another rest of the 3 arms has a 0 probability. And also this will be the same, the 0 average is 0. So what happens if we just place EPS value to 1, that means 100% that will explode. So in the time, if we run the code and see the graphs outputs, then we'll see that is yes, the average rate is 0.5. And as this is 100% exploration, and there are 4 machines, so each arm has to be chosen in 25% time. So this is the average of arm pool average, that is 25% time each arm has to be chosen. So if we just place full exploitation, then only arm 1 has to be chosen. And if we place full exploration, then all of the arms are chosen equally. But if we place any value in between 0 and 1, that is 0.2 and 0.3, that means the agent will decide which arm should be chosen for maximum reward, and that will be just changed to the probability of machine 4, that is in between 0.6 and 0.8, and that will vary on the value of EPS. So that's it. So that was the multi-arm bandit problem. So where there is some option of a mixture of exploitation and exploration, then the agent will just train the model in such a way that is the agent will be able to decide which arm or which machine should be chosen for maximum reward. So that's it. Thank you. Thank you for today.